All right, good morning. It is 11:20 and you know what that means. It's time to thrill and excite you with awesomely cool mathematics and get you guys pumped up for the wondrous and awesome raw power that is math that helps us absolutely dominate our universe and stop the toads from becoming the superior race, if you know what I'm saying. But if you don't know what I'm saying, welcome, good morning, and let's do some cool stuff today. So we've been doing some stuff with vectors, and it's just like, well, why are we looking at it in terms of vectors? Well, because when we change the way we look at things, it has just profound implications on what we can do with it. And one of the things we can do with it is we can better use complex numbers. And unfortunately for you guys were taught complex numbers with really kind of in a vacuum without really an understanding of why do we have imaginary parts of numbers, right? And so I really want to make sure, and I'm gonna zoom out here. So I usually have my classroom and we have stuff. So with imaginary numbers, remember we often think of the y-axis and the x-axis. Ooh, I should go this way. The y-axis and the x-axis, and that's a two-dimensional plane. But we have to remember that even with two dimensions, you can have two-dimensional planes interacting in a three-dimensional world. So a good way of thinking of that is think of a cog, right? A cog is a piece of machinery that goes around in circles. Have you guys ever seen a cog before, right? And they have little grooves around the outside of the circle, and then it goes around like this, has little teeth, right? So a cog goes like this, and it's going around. Okay, now a cog is a representation of a two-dimensional plane, right? You have a circle, and it's going up and down, right? We've been doing that with trigonometry, right? Sine and cosine, it makes a circle. But what if you introduce a new cog that interacts with it here? Let's see if I can do this. Oh, this is hard. Oh, it's so hard. It's so hard. Okay, so basically you have a cog going up and down like this, and then you have another cog going like this, and it's going this way. So they're in two different planes. This one is going in and out like this, and this one's going up and down like this, right? It's kind of like patting your head and rubbing your tummy at the same time, right? Okay, now what's happening is, well, we're talking about this one, right? But as this one's going, do you see how it interacts with this one going in a different plane? And that's what imaginary numbers can help us represent. The idea is that we're looking at a two-dimensional plane, but there's parts of that thing in that two-dimensional plane that are interacting with another two-dimensional plane. So imaginary doesn't mean, oh, here, you guys don't need to look at me anymore. That's weird. Imaginary numbers aren't imaginary. They're not make-believe. They're just in a different plane, right? So you have what you're looking at in your plane of existence, but then it's also interacting with another two-dimensional plane. So it's how two-dimensional things interact in three dimensions, okay? So that's really important to know, okay? So the complex plane. So to remember what a complex number is, a complex number, you have a real part and you have an imaginary part, okay? So, and what that just means is that you have a part that's in the plane that you're looking at, and you have another part that's not in the plane that you're looking at. So what we can do is to visualize complex numbers, we can look at a Cartesian plane, but instead of y and x, you have your real and you have your imaginary. Now, I agree, like, why do we call it imaginary? So the reason why they call it imaginary, if you ever read a book, it's called, oh my gosh, Flatlandia? Oh no, now I don't know the name of it. Okay, well, regardless. Anyway, there's this cool book, and it just talks about what life would be like if we were two-dimensional. I know Wrinkle of Time touches on it a little bit. But imaginary axis, right? So that's now this axis. So you have your real numbers and your imaginary numbers. So, for example, let's say I had a point at 3, 1. Okay, on this graph. Do you guys see where we're going with this? It's a vector, isn't it? Okay, and so what that means, this is the same as 3 plus I. Okay, Now, this is going to get really cool because now what we can do is we can make more understanding of what the heck a complex number is. Because a complex number has a real part, but then it has a direction off of that real plane. I hope that makes sense. So one thing, do you see how I'm drawing this all in one plane, right? So imagine then the imaginary axis is actually coming out of the paper and it has some direction, right? So now what's really cool is you have, think of like the hair. I don't know if you guys can see the hair in my arms. When it's flat like that, it's in the plane of my arm. But if I go like this and I get all the hairs, right, they stick up. And so they're sticking up in a different plane that my skin is not aware of. And so to my skin, it's an imaginary plane, right? So that's what's happening, right? And then the way that my hair sticks up on my hand, right, it's going to have some angle, and the magnitude is going to be the real part and the imaginary part. I hope that makes sense. It's kind of creepy that I'm just showing you my hair and rubbing it, but are we doing okay? Does this making sense? I just wanted to make sure you guys know that. Okay, I want to name drop something really quick. So this is just an aside here, but we have to remember what conjugate means. Okay, so conjugate. So just remember, if I have A plus BI, the conjugate, oops, I swear, conjugate, the conjugate would be A minus BI. Okay, so another example, if I had A minus BI, the conjugate would be A plus BI, right? So you're just changing the sign in front of that. Conjugates are really important because they allow us to take imaginary it allows us to take complex numbers and get real solutions. Because just because my hair, right, just because my hair has an imaginary part because it's going up, it still intersects on the real plane. So it has a real root. So we want to be able to take complex numbers and get real answers, right? So part of doing that is using conjugates. So I just wanted to name drop that so you guys are aware of what a conjugate is. Okay, how am I doing so far? All right. The next big thing, and this is all 6.5, by the way. We're only doing a little bit of 6.5. Okay, so the next big thing that I want to talk about. So this is how we use this is how we use vectors in the complex realm. Okay, so the next thing I want to talk about is the absolute value. So the absolute value of complex numbers. Now, we couldn't have talked about this unless we talked about vectors, because it turns out that complex numbers are defined as vectors. And that's crazy, right? So if I want to take the absolute value of BI, right? And normally we think, right, you're told absolute value is the distance from 0. Well, in this case, the distance from 0 is the magnitude. Okay, right? So the distance from 0 is the magnitude. Now, this has a different word than magnitude. It's called the modulus, and I'll talk about that in just a second. So this is the square root of a squared plus b squared. Right, and the reason why there's no I here is what's I squared? I squared is just 1, right? So I just want to point that out. The reason why there's no I here is because I squared is 1. Okay? All right. This value is called the modulus. So it's called the modulus, right? And that is just the aka the magnitude. So the magnitude of the vector. Okay, but it has a special name for complex numbers because it's used so much. So it's called the modulus. But I'm just going to put this Because if you can remember the modulus being a magnitude, then you're going to do so much better. Okay, it's just going to stick. Okay. Now, some people want to be like, well, why is this true? Well, here's a quick little proof for you. So here's a proof. So let's say I have 0 imaginary parts. So that's the square root of a squared plus 0 squared. So that's just the square root of a squared. Well, don't we lose an answer here? So it turns out that's just the absolute value of a. Because remember, absolute value of a is plus or minus a. Okay. So if you're like, whoa, yeah, right, this is just the absolute value of a equals absolute value of a. Okay. What happened to the 0? That's a great question. So 0 means nothing. So these are the same. Right? A plus nothing is just a. Yep. Okay. So the absolute value of a complex number is the magnitude, is the modulus. Okay? That's what I want you to get from that, okay? And that's really important. So again, the takeaway here is the absolute value of a complex number is called the modulus, which is the magnitude of a vector. Now, the reason why they call it a modulus is because just because you have complex numbers doesn't necessarily mean you're talking about vectors. Does that make sense? That's why it has its own name. But the thing is that you're hardly ever going to use a modulus, which is you might use it, but you hardly are ever going to use it without a vector. Okay? So that's why we're doing this. So again, we can write complex numbers in the imaginary plane. Okay, so we have the real and imaginary axis. This is called the imaginary plane. Okay, and we can do it as a vector. So everything holds true with vectors. Now, if we want to find the magnitude or the absolute value of it, right, that's what a modulus is. Okay, that's what the modulus is. And this is a little proof that it works, right? So the absolute value of this is the square root of this. And it turns out the absolute value of a really is just the square root of a squared. Next class, when we start getting into conics, because it's funny, the way that we learned about parabolas and exponentials is actually backwards to how humans actually found them. Okay, so that's why we're going to go back and do conics to end the year off, right? So that's what's going on here, right? You think absolute value is just a standalone thing. No, absolute value is just the square root of a squared, and that will make sense when we do conics. Okay. All right, cool. So just really quickly, right, adding complex numbers. So adding, subtracting, multiplying, everything is the same for complex numbers. So if we have two complex numbers, so let's say I have u equals 1 plus 3i, and I have v equals 2 plus I. Okay, graphically, right, if we were to look in the imaginary plane, right, so that would be 1, 3. Right, that's u, and then v would be 2, 1. Right, that's v. Right, so this is my imaginary axis, and this is my real axis. I'm sorry, that's an I. Okay, so when I'm adding these, remember what we're really doing is we're just taking this v and we're going like this, and then we're finding the resultant. Does that make sense, guys? So it's the exact same thing we've been doing with vectors before. So you add the x components, and you add you add the real components, you add the imaginary components, and you guys probably already did that in an algebra class. So my resultant vector would be 3 plus 4i. Okay, so again, you combined the x and you combine the imaginary. Sorry, not the x. You combine the reals and you combine the imaginaries. You guys doing okay? I'm kind of speeding through this section because there really isn't much more to it than just what is a complex number as a vector and this absolute value thing and modulus. Okay, because modulus is going to be really important, guys, because modulus, now you guys ready for this? Remember how we were doing all those physics questions? So modulus is your magnitude, right? So modulus is like if I was talking about physics and this was force, it would be the amount of force, right? So modulus is your amount. So when we take absolute value of a complex number, that's our amount, right? So because we have this amount that is partially in my real, and so if I was talking about my hair, right, the modulus would be how much hair is in that hair that's part in my real, part in my imaginary plane. Okay, so I hope that makes sense. I'm trying to do my best, but you guys probably are like, come on, Kref. Let's take a look at 6.6, and I agree. Let's take a look at 6.6, and then if you have questions, please come see me, come talk to me, and do that. Okay, so let's go into 6.6 now. Holy moly, someone's joining in. That's gonna be a bummer. All right, so 6.6. So now we're gonna talk about the trig form of complex numbers. Okay, and so you can see what we're doing here, and this is why I wanted to get 6.6, is what we're doing is we're taking everything, we're putting it together now, right? So we did trig form of vectors. We can think of complex numbers as vectors. Do you guys see why I had to do a little quick intro to 6.5? So when I say trig form of complex numbers, you might think, oh, that's a lot like trig form of vectors. Okay, so the math is the same. The math, the logic, everything is the same. And that's one reason why we did vectors, right? So now we can start looking at, right, do you guys see how we're starting to get into 3 dimensions, right? Because when you start talking about complex numbers, you're talking about how do 2-dimensional planes interact with other 2-dimensional planes, right? Which is 3 dimensions without doing 3 dimensions. Okay, so to do this, we have a formula. So the general form. Okay, so for the trig form, so what we have is we have z equals r times cosine of theta plus, I hate when they do this, sine of theta times I. I don't like putting I in the front. I always think you should put I at the end. Now, I get why they do that, because they don't want you to think that the theta is in the imaginary plane. Does that make sense? But your book puts I in the front. Whatever, they do them. Let them do them. Okay? So, what does everything mean? Okay? The R here, okay, Z is your complex number. Okay, and no, complex number isn't a status on Facebook. Hey man, how you doing? I don't know, man. It's just really complex number right now. No, sine and cosine are not multiplied by 1. Okay, I. So take a look at this. What's my y-axis? My y-axis is imaginary. So if I take a look at my imaginary axis, right, and I take a look at my cosine, only my sine is imaginary. That was a great question. Does this help you out? Do you see how only the sine is in the imaginary axis? Right? Because sine means up and down. So a lot of people, they're like, they just memorized, oh, sine is y. No, sine means up and down. Okay, sine means up and down. So now only the sine is imaginary. Okay, and the cosine is still real. Okay, so, and that's what we're going for, right? So this right here, this is my imaginary part. This is my real part. Okay. And that's why I had to do 6.5 first, right? I just had to show you, hey, this is how you represent this on the imaginary plane. Okay, now, what the heck is R, right? What's going on? Okay, R is your modulus. That's why Kreft made a big deal of it. That's my modulus. Now, does this make sense? Yes, this makes absolute sense. Because isn't the modulus just the magnitude? And think about that. When we were doing physics problems in your homework, didn't you just take your magnitude times cosine for your x and then times sine for your y? Right? That was your homework, right? With the chains, right? You had to break it up into the x part and the y part. So it's your modulus, right? And modulus just means you can think of it as magnitude. It's a little bit different than magnitude. That's why it has its own name. But I mean, this year's crazy, so I'm gonna lie to you a little bit and just be like, think of it as magnitude, okay? Which you can. This is a good lie to have. And then cosine and sine, okay? How are we feeling right now, guys? Am I doing an okay job? Am I explaining this? I mean, of course, as always, right? It's gonna make sense now, and then you're gonna go to your homework and be like, what happened? My face is melting off. Right? It's going to be like Indiana Jones, right? Where all their faces melted off. Okay. So, I think I'm losing my mind a little bit. Yeah, check. Okay. So, let's do this. Let's see what we can do with this, okay? Let's see what we can do with this. But that's your bread and butter, guys. Oh, some more things. Theta, instead of the angle of direction, it's called the argument. Okay. So again, we're really getting into technicalities here, right? So because we're technically going into a different plane, it's no longer called the angle of direction, because remember, angles are defined in a two-dimensional plane. Well, if we're going between dimensional planes, then angle is no longer defined. So now it's considered the argument of z. So it's the argument of the complex number. So we have the modulus and we have the argument. Okay? Like, come on, math people. Really, this is the best you could do for naming? I get it. But I'm not famous enough to change words in math. All right, here we go. So, let's try this. So we're going to, so here's example numeral uno. So I'm going to have, we're going to write a complex number. Sorry for my shorthand. Complex number into trig form. Okay, let's just start basic. So we're going to write a complex number into trig form. So my complex number is z equals -2 minus 2 root 3i. Okay, so this is a complex number, right? You can see this as a plus bi. And we're going to write this in trig form. Okay, so to do this, the important part here, there's two important parts. We need to find the modulus and we need to find the argument. Okay, so we got to find those two things. So first, find the modulus. And remember, the modulus, right, is the absolute value of z, right, which equals the square root of a squared plus b squared. Now again, why isn't the I with b? There's an I here, right? Remember that I is defined as -1. Okay, so -1 squared is just 1. So that's why the I goes away. Does that make sense? You guys are cool here, right? So you guys know that I equals -1. So then I squared equals 1. Right? And remember, so why does I equal -1? Because it helps us describe what happens when you have the square root, when you have a negative answer for that. That's all it is. It's like what happens when we have negative roots, roots that don't exist. So this byte right here, I came about because of a necessity to explain phenomenon like this. Okay? All right, so we're going to find the modulus. So the modulus then, here, I should get out of that color. the modulus here for our problem is going to be the square root of negative 2 squared plus negative 2 root 3 quantity squared. Okay, so this is going to be the square root of negative 2 times negative 2 is 4. Negative 2 times negative 2 is 4. Root 3 times root 3 is 3. 3 times 4 is 12. Oof. Brain fart there, guys. Oh, it was a close one. 4 plus 12 is 16. Square root of 16 is 4. Goodbye. All right. There's our modulus. Okay, so the reason why there's not an I here, I mean, technically this is bi squared. But what's I squared? I squared is 1. So instead of writing bi squared, we just write b, because whatever b squared is times 1 is just going to be b squared. So we're not going to have a square root of 1 because technically speaking, this is the square root of a squared plus bi squared. Well, if you have bi squared, then what's I squared? I squared is 1. It's just b squared. Does that answer your question? So there's not going to be an I anymore, right? As soon as you square this imaginary term, the I goes away. It becomes real. Did that answer your question? You can turn on your mic. That might be quicker, just to be like, hey, that helped or didn't help. Okay, well, I'm not hearing anything back from you, so I don't know if I helped you or if I didn't help you. So again, the reason why we don't have an I in here, right, is because when I go bi squared, I squared becomes 1, so it's just b squared, right? So there's no, this is all real. Okay, Constantine, that's funny. You weren't the one who asked. You guys are great. All right, well, I'm not hearing back from you, so I'm going to move forward. Okay, so I have this modulus, okay? So the second thing I want to do, sorry, I'm not really linear here. The second thing that I'm going to do here is I'm going to find the argument. Okay, so to find the argument, it's the same thing we did before, right? So I have an imaginary plane, so I have real and I have imaginary. And I'm going to be in the third quadrant. Right? And I'm going to have to find the angle. Now, remember, if I do this in a calculator, I'm going to be finding this angle right here. But I don't want that angle. I want it from 0 degrees. I want phi. Right? So my argument here will equal phi. But I'm going to find, right, my calculator is only going to find this angle. Right? So I'm going to use right triangle trig to find this angle. So remember, this is down 2 root 3 and left 2. So if I use this, I'm going to know that tangent of theta equals negative 2 root 3 over negative 2. I'm going to try to go slow here because I know some people get lost here, right? Does this make sense? I'm finding this angle right here. So I'm going to have theta equals tangent inverse of negative 2 root 3 over negative 2. But then I have to remember the argument that I want is really this. Okay, so it's going to be, I'm in degrees, it's going to be 180 degrees, right? So theta is going to equal 180 degrees plus theta. Okay, right? Because I'm going to go 180 degrees and then I'm going to go this extra theta. So let me grab my calculator. And like, I hope it blows your mind that we're doing this with imaginary numbers, right? Pretty cool. Pretty cool. I mean, yeah, it's pretty cool, Kraft, you know. But, you know, it's not like lifting weights cool because, oh my gosh, Kraft, you suck. Oh my gosh. Okay, I lost it. All right, here we go. So much pressure. Everyone's looking at me. Okay, negative 2. I could have gotten rid of the negatives, right? Because the negatives are going to cancel out. But I didn't. It's just what it is. So let's see what we got. 60. Okay. So I'm going to plug things in. So I get theta equals 180 plus 60 is, what is that? Of course, the book did it in pi radians, so I can't cheat. All right, plus 180. So 240. Right, and you guys could have done that in radians as well. Thanks, Constantine. I appreciate you. More than you know. All right, cool. So I did two things. I found the modulus. I found the argument. So now I can bring it all together and I can get my answer. So my answer is going to be z equals my modulus times cosine of theta plus sine of theta I. So I'm going to have z equals 4 times cosine of 240 degrees plus sine of 240 degrees I. This is my complex number in trig form. Okay, and remember, this is giving me way more information than the complex number because it's giving me how much and it's giving me what direction. Do you guys have questions? Does anybody have comments? Man, 50 minutes is not enough time. We're at 12:10, right? So I would love to do another one of these. So I'm going to move ahead and do one other example. And if I have more time, we can vote. And you guys can tell me if you want to do another one like this or another one like next one. It's not harder. It's just the opposite direction. So we're going to go from trig form to standard form. Yeah. I mean, that's really all I have time for today, right? You guys are expecting me to like tell you how to give you the math to make a nuclear warhead, but I can't today. Maybe in the future, okay, when we have more math. It's actually not too hard. Really, the hard part of a nuclear warhead is the shaped charge and the weapons grade plutonium. Everything else is actually pretty simple. Okay, so let's go on here. This meeting is being recorded. All right, so let's do example 2. So in example 2, we're going to do the opposite. So we're going to write a complex number in trig to standard form. So let's do it. So we're going to have z equals the square root of 8, because nice numbers are boring, let's change up my notation a little bit. I'll use what the book's using so that we guys can have this. So I'm going to have negative pi over 3 plus sine of negative pi over 3 I. Always feel like I'm voting, you know what I mean? Like I. Okay. All right. Are you guys ready for this? Do 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 do. Are you ready for this? Do 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 do. Okay. It's really actually this is easier. You guys ready? Just make a triangle. Just make a triangle. And then Kreft goes and makes a couple of mistakes. Okay, so the reason why I made mistakes is the angle tells me what quadrant I'm in. So negative pi over 3 is going to be down here, right? Okay. And then if we fill things in, my magnitude or my modulus is square root of 8. And then this is my A and this is my B, right? Because this is real and this is imaginary. You guys see how that worked? You guys with me here? So I'm just drawing a triangle, right? So I know that my angle is negative pi over 3. Thank you, I appreciate this, guys. And then I know that the A is my real part, the B is my imaginary part, and I know my modulus is square root of 8. So cosine of negative pi over 3 equals my adjacent over my hypotenuse. So I don't want to be that guy, but remember how I said it's exactly the same? It's just the modulus times cosine of negative pi over 3. So really what you're doing here, don't you guys see that we're just distributing the square root of 8? So I did all this visual, but you don't need to do the visual. I just did the visual to make sure you guys understood why. But you guys see how we're just distributing the square root 8? Right? We're just multiplying, right? And so I could show the same thing, right? So this is going to be my A, and then square root of 8 times sine of negative pi over 3, that's going to be my B. Oh, and there's an I here, right? There you go. Pretty cool, huh? Like, complex numbers are like, I mean, you don't have the math and the trig when you first get introduced, but this makes a lot more sense with complex numbers, what they are, what they do. Okay, so take my calculoid. Yeah, surprisingly, right? Like, yeah, well, and like what sucks is like you were taught imaginary numbers and like you weren't told what they are, what they're used for, or how they exist, or why even. You're simple. No, that's a joke. I would never. That was just a joke, guys. Stop using chat to say hi to everybody, or else if someone asks a question, I won't be able to see it. Sorry, that sounded like I was angry about it, but I'm not. Okay. Not a big deal. Okay, I'm going to type that in. So I get A is, oh gosh, that's an ugly number. Does it want us to round? Oh my gosh. If you type this into a calculator, you're going to get a decimal. Okay, so we're going to do this by hand. Cosine of pi over 3, that's root 3 over 2. No, that's 1/2 root 3 over 2. Okay, so then cosine would be the same. So this would be root 3 over 2. So this would be root 8 times root 3 over 2. Root 8 can be broken down because that's really 2 times 2 times 2. So this is really 2 square root 2. This is really 2 square root 2 times root 3 over 2. The 2's cancel out. And then I get okay, easier way to do this by hand. So to do this by hand, this is how I do this by hand. I would just do these first. So let's do a unit circle. So I know this is root 3 over 2, 1/2. This is 1/2 root 3 over 2. It's negative, so this would be 1/2 negative root 3 over 2. So this is root 8 times 1/2 minus root 3 over 2i. Okay, so do you guys see how I'm doing this? Ooh, there's a question. Yeah, the I is a placeholder so that you know it's in the imaginary plane. That is an absolutely astute observation that you made. Yeah, that's why the I is there. It's just a placeholder to tell you that you're in the imaginary plane. And I is always equal to -1. Absolutely. Okay. So, right, that's what this is, that's what this is, and then you can multiply by root 8, so I get root 8 over 2 minus root 8 root 3 over 2, and then, so that's root 8, so root 8 is the same as 2 root 2, so I get root 2 over 2 minus 2 root 2 times root 3 over 2, so the 2's cancel out. So then I get, and there's an I here, so I get root 2 minus root 6i. So that's how you do it by hand. Because if you did this by a calculator, you would get a decimal, and it's irrational. So that adds a bit of complexity to it, not to be punny with my words. Okay. Was that too much? Did I do too much too quick? Maybe I got excited with solving this by hand. And the reason why to solve this by hand is that the answer is irrational, right? So what I did is just cosine of negative pi over 3 is 1/2. Sine of negative pi over 3 is root 3 over 2. Then I multiplied by root 8. I know that root 8 equals 2 root 2, right? Because root 8 is the same as root 2 times 2 times 2. So I can take a group of 2 and pull them out. Then the 2's canceled out, and then root 2 times root 3 is the same as root 6. So that's how I did that. You guys are awfully quiet, so does that mean I did too much, too fast? That's usually a good sign, right? Like when everyone is awkwardly quiet, no one wants to speak up and be like, Kreft, actually you went way too fast and I have no idea what's going on. And I appreciate everyone who gets it, but just remember, for everyone who gets it, there's always someone that's going to be like, Mr. Kreft, no say. Okay. So do you guys want me to do one more of these, or do you want me to do one more of the previous ones? So vote. If you want me to do one like the first one, type 1. If you want me to do another one like the second one, type 2. Of course, you guys are 50-50. All right. Well, I'm going to start with doing another one just like the second one, and then I will do another one if I have time. Okay? Sound good? So here is example 3. So this is going to be like example 2. Okay. So we're going to have z equals 5 times cosine of 7 pi over 6 plus sine of 7 pi over 6i. And again, the I is telling me I'm in the imaginary plane. Okay. So let's go ahead and do this. So again, I'm going to convert this to a plus bi. Okay, that's my goal. So I'm in trig form, and I want to get this to standard form. Okay. Now, I drew the picture just so that you guys understood what was happening. But what we're really doing here is we're just multiplying these like this. Okay. So the easiest way to do this is to do this by hand, if we have numbers, is to figure out what the heck these are first. So I'm going to draw a unit circle. So I know this is pi over 6, so that's 2 pi, 3, 4, 5, 6, 7. So this one right here is 7 pi over 6. Okay, so I went 1, 2, 3, 4, 5, 6, 7. So let's figure out what this is. So if this at pi over 6, this is root 3 over 2, 1/2, then this is negative root 3 over 2, 1/2. So then this is negative root 3 over 2, negative 1/2. Okay, does this make sense how I'm using the unit circle, guys, right? I know this one, this is pi over 6. So there's symmetry straight across. So then this one is just the x is now negative. And then I go down from that to get more symmetry. And so now the x and the y are negative. So what's cosine of 7 pi over 6? Negative root 3 over 2. And then what's sine of 7 pi over 6? It's negative 1/2. Okay, and I'm glad I did this because look at that root 3. My answer is going to have an irrational part to it, right? So that means I'm going to have to do something. So let's take a look. So now I distribute. So I get negative 5 root 3 over 2, and then plus negative 5 halves I. Now, in this case, I can't simplify anything, right? I can't simplify anything. So this is my answer. I can just write this as 5 root 3 over 2 minus 5 over 2I. And we're done. Okay, so the hardest part here is figuring out what these things are on the unit circle. Okay. And your homework is in radians. Okay, which is radical. All right, so anybody have questions before I do example 4? Anybody have questions? Okay. Yeah, the unit circle is hard, and I totally agree. And that's why we spend so much time normally on the unit circle, because if you just try to memorize it, you're not in a good place later on, right? And that's why we tried so hard to be like, understand it, but it's hard to do, and it's hard to convince teenagers to do that. But yeah, understanding the unit circle is like, you have to in order to do trig. All right, like example number 1. All right, so we have a complex number z equals negative 3i. And we're going to get that to the form z equals r cosine of theta plus sine theta I. Okay, so in this case, we don't have a real number, right? So in this case, we don't have a real number. But first, we want to find the modulus. Modulus. Okay. So you want to find the modulus. So to do that, remember, it's the absolute value of z equals the square root of a squared plus b squared. There's no I because I squared is 1. So this is just going to be the square root of 0 squared plus negative 3 squared. Remember, the 0 squared is just 0. So I'm going to get the absolute value of z equals 3. Yeah, 3. Because we're talking about absolute value, so the negative doesn't matter there. Crazy, right? Almost had a heart attack. All right, here we go. So there's our modulus. Then, part 2, we're going to find the argument. Okay, some of you guys are really good at finding arguments with your parents, so you should be good at this. So, that was a joke. The argument, remember, is the angle. So if I was taking a look at this, right? So this is my real. This is my imaginary. Negative 3i, so it's just up 3. Oh, it's negative. Okay, so there's my thing right there. Here, I can make it a different color. That's too late. It's just turned black, right? It's just down 3, right? Okay, so what angle? I mean, you don't have to really do much here. What angle is that? Right? That is 2 pi. No, 3 pi. Gosh dang it. 3 pi over 2. Okay, so I found my argument and I found my modulus. So now I'm going to write this as z equals 3 times cosine of 3 pi over 2 plus sine of 3 pi over 2i. So that one was actually pretty easy because it didn't have a real term. Right? If it had a real term, then we would have had to do the triangle, and then we'd have to be careful with, am I finding theta or am I finding phi? It is 12:11, so I'm just going to